Good. So we had, before going to this bigger picture view, we discussed branch prediction. I give you the insights and the circuitry of the branch prediction. But now it's worth going through one example. Right? Let's go through one example, especially as a preparation for the midterm. How, well, also in lab 2, you also experimented with the tables, whether it's PTB or the branch predictor, the G-share one, right? So how do we really keep history? How, through the table, we are able to predict whether the coming one is taken or not taken. And taken means I jump to the branch target, not taken means I don't jump and I execute the subsequent one, right? So assume I have an example like this. I have two nested for loops, I and j. First one executes 100 times, the second one executes 3 times. Good. And assume my branch history table. Something important here is that these examples are not for the BTB. Remember, in the branch prediction, we said we have 3 questions we need to answer. What are these 3 questions? Can you mention one of them? Yeah. Yeah, if we jump or not, which is taken or not taken. Yeah, okay, so you want to say the same thing, okay, yeah. What is the next target address? So basically, the target address of the branch, this is a branch. There was the very basic first question. Yeah, whether the instruction itself is a branch or not, right? So we start by saying, okay, whether the instruction is a branch or not, and if it's a branch, what is the target address? We said these 2 questions are answered by. Yeah, okay. So that, okay, in fact, there are 2 tables, not 1, right? And this is why you set them separately into sub-questions in the lab. There is the BTB. So we already, kind of in the tutorial, we went through that flow diagram here, right? So we said these are the 3 questions we want to answer. Is the instruction a branch or not? And if it's a branch, whether I should jump or not, and what is the predicted target, correct? These 2 questions are addressed by the branch target buffer. That's one of the tables we have in the lab, BTB, right? See, what BTB stores is simply you have a very simple table. We had the format of that one here. That stores here. That stores, you access this one with the program counter, and then it tells you whether the current instruction is a branch or not, right? We said this tag because multiple program counters can be mapped to the same place, but it's a bit of a detail. Ignore about this one now. And we said BTB can tell you whether this instruction is a branch or not, but also it tells you the target address if you add the target address to the table, right? If you do something like that. You have whether the instruction is a branch or not, and if it's a branch, what is your target address? Good. So BTB answers the 2 questions to me. That is, again, these ones, right? But still, I don't know if it's a branch and this is the target address. Should I jump or not? This decision on its own is in fact harder than these 2. And this is done by the branch predictor. Usually, people refer to branch predictor as it might be the combination of both sometimes. But in reality, we separate them and Maxim separates them because they are 2 different techniques, right? For example, BTB is a simple hardware component that in fact solves the problem most of the time because you cannot do better. So this is almost a dead area of research, BTB, because I keep a simple table. I have the program counter during the fetch stage. I have a flag telling you whether it's a branch, and if it's a branch, what is the target address? Good. The harder part, and why it's harder because it comes later on in the pipeline, whether the condition is true or false. And in that case, I need really to do more circuitry, more intelligence, which is done by the branch predictor. Maxim implements the G-share branch predictor, but in that tutorial document I shared with you, they discuss all the possible ones, right? And these are the tables that we're going to discuss right now. I'm not going to cover much the BTB because, as I said, BTB is a simpler, it's just a simple operation, right? And it has very high accuracy most of the time. Because if you have, the idea is that if you have loops, if you store the program counter before, you are sure it's a branch, right? If you only store it before, you make a guess and then you correct yourself later on. So it's a prediction, but it's a more, you are either correct or wrong. There is no, a lot of history or a lot of machinery work you need to do. Good. So you see the difference between BB and BTB, right? So again, BB or branch predictor is the one that tells me the condition result. BTB is the one that stores these 2 things. Good. What we are going to discuss now is, in fact, the branch predictor side of things. right? So how do I determine my condition, whether it's whether I should jump or not, or in the terminology of branches, whether it's taken or not taken? Good. I guess I was asking a question before I answered the question. I forgot what the question I asked. So, yeah, okay. So what I was going to say is that what we have in the lab is G-share, which is a more complex dynamic branch predictor. We're going to discuss some of the simple solutions here, but all of them are based on history maintenance, right? One of them is called branch history table, BHT. You will not find this terminology in Maxim, because Maxim, or it might be naming it inside G-share, but BHT is one of the simplest branch predictors, right? Because you keep one bit of history, and simply if it's 0, it means not taken. 1, you predict it's taken. To understand how does it really work, we have that running example here. We said we have 2 for loops, which means you have 2 branches, right? And then the state time is simply, well, that's the truth, that's the outcome. So what happens now? You're going to update your state later on, because this is what you use to really correct yourself after you resolve your branch. So we said the way the prediction works is that you predict early in the pipeline, but once you figure out the deterministic correct answer at the execution, you have to correct yourself if you were wrong, or affirm that your prediction was correct if it was correct. So usually the correct answer is used to either keep status, like to, for example, track the accuracy of the branch, or to correct yourself over time, or both. So this is the real state based on the previous outcome, and this is my prediction. If you want to understand what is happening, let's start by saying, I say start my prediction as not taken. Okay? So simply not taken means ignore the branch and continue what's after. Then, if I go inside that for loop, initially I is 0, which means in fact it's going to be taken. I execute the for, right? Good. So if it's taken, I turn it out to be wrong. So this is basically my status tracking. I did a misprediction here. If I am wrong, I have to update the state time from the previous one, right? Because I used the old branch prediction, the directly before one, to predict the new one. So BHT is as simple as what happened in the past one, you assume is going to happen for the current one, right? So this is the past branch. This is your prediction for the current branch. This is the actual outcome after you execute your condition. So in the past, well, you assumed you were not taken. In the initial state simply there was no past, so just not taken. Here, the past was taken, so you update it. And because I predict based on the past, so I'm going to predict it's taken. In that case, it is taken. Why is reality taken? Because you executed that for loop, I equals 0, you go to the second one, j is still less than 3, so it's also taken. So in that case, you are correct. If you observe, you remain in fact correct for 2 times, because the j will execute for 3 times, correct? Take it, take it, take it. And then you will predict it's taken, but you reach your loop limit. In that case, you predict it's taken, but in reality it will be not taken, because j is equal to 3. In that case, you are wrong. And then you update your state time to be not taken. Once I finish the inner loop, I go to the outer one. Am I done? No. I is in fact less than 100. So I predict not taken, but in reality, I'm taken. You start seeing the pattern? So I predict correct twice, and then wrong twice. Why that's the case? Because here, the inner loop only has an iteration of 3, which is very small. We mentioned in the past, most of the branch prediction happens because you execute loops, for example, for a very long time. So your corner cases happens in a very small percentage. Right now, it in fact happens 1 every 3 executions, right? So it gives you a bad performance. And what increased also the problem with this, and this leads us to the second branch predictor, is right now your prediction is mixing 2 branches together, right? Because once, for example, here I predicted it's not taken for the j, but my second branch was the I, which has a different limit. Okay? Questions? So, for example, if you were given a problem like this, how to start? First of all, you start from any initial condition, it doesn't matter, or it's given to you. You say, for example, assume it's not taken at the beginning. And then you start building up your actual execution, the outcome, you see whether you were correct or wrong, and then you update yourself accordingly, and you start going through the prediction. That's also a good question we discussed earlier when we talked about hardware software code design. The program knows, the software knows, the hardware doesn't know, right? And that's one of the problems of doing these things purely in hardware. The hardware does not have the global view of the program. It only sees a BEQ with registers and the label to jump to. It doesn't have the semantic that, in fact, this loop executes for 100 times, right? And in reality, well, it's not something related to the branch prediction, but in fact happens for so many things. I currently have a graduate student that's working on a similar problem, saying most of these loop iterations, in fact, are known at compile time. The hardware loses the semantics. So if we give this to the hardware, then the hardware will do more or way more intelligent decisions, right? So in that case, for example, if I told the hardware, well, this is executing 100 times, 3 times, you almost right now is not doing a prediction, but rather doing something as if you know the future, right? So it's like an oracle view. But current ISA contract, or the semantics between the software and the hardware, does not convey this information, right? You only operate at the instructions level, which is a very local view of the execution of the program. Good? Good? Okay. Yeah.
So what was this table used for?
Yeah, this table is used for you make a prediction, right? For the branch. So you have a branch, and where do I do that? You either do it at the recovery stage or at the fetch stage. So you don't wait until the execution happens. This is where the execution is really happening, so you update the table later on, right? And in Maxim, you're asked also to figure out when does Maxim do the prediction and when does do the recovery, right? Yeah. Good. But we also answer them in the lectures anyway. Like you usually do the recovery for the branch predictor at the execution stage, because this is where you really execute your condition. This one either has an N or T. It doesn't tell you what branch is that, right? It's just one bit, 0 or 1, right? So this is why it also makes these two together. Good. So again, the limitation here is that I jump too fast between taken, not taken, and my corner cases of the loop is not allowing me to really start learning. So I don't reap the benefit of correcting myself, because once I correct to one direction, well, the program execution, in fact, would switch to the other direction soon, right? So here, what is my accuracy? If I ask you to calculate the accuracy, yeah, 1/2 is 50%, right? How to calculate the accuracy is simply the times you are correct over the total time, right? So you are correct half of the time, yeah.
There would be like more history in play if the second loop was a lot larger. Then we'd see like a more
you mean more correct results?
Because right now it just looks like
exactly. If this one was larger, this is why I said, okay, this case is showing the problem with that thing, is that you're not giving the hardware enough time to build in the history that reaches a stable state. Once you correct, you turn out to be wrong again. Right? Okay. Now, because you shift too soon, then people said, okay, I'm only using 1 bit. Why I don't increase the history such that I don't shift too soon? And here we have what they call 2-bit saturating counter, or 2BC. Instead of using 1 bit, you use 2. And instead of jumping directly between taken and not taken in the bit based on the previous one, you make a more, I would say, slow and steady decision. I switch only if the previous 2 had a certain battery. How to do this? We come up with a notation of big N, big T, and small n, small t. And simply because these are 2 bits, you have 4 combinations, right? 0, 1, 2, 3. 0 here means 0, 0, right? So if you look into the previous 2 executions of a branch, they are either both not taken or one of them is taken, etc., right? So these are the 2 combinations we have. This is the direct previous one. So this is basically previous, and this is the other previous one, maybe -1, -2, if the current one is B0. Then I would say if the previous 2 were in fact not taken, this is a more strong decision that I would predict that I'm not taking, because now it's based on my previous 2, not previous 1. So in that case, it will be capital N. But then if I was capital N, and then, which means the previous 2 were zeros, but I turned out to be wrong, so I turned out to be taken. Now my previous 2 will be, for the coming one, will be 0, 1, right? Instead of moving directly to taken, you do a smoother decision. So you say, okay, I'm going to move to a state that I call N small, which means I don't jump directly from N to T, but rather go a transition that I'm going to predict it's not taken, but I'm not very sure, right? So if you look into the levels we have right now, at the strongest point, you are T. and the other extreme you are n capital, but then this is n and this is t. And you say, I move from here to here slowly, not based on a single prediction, but based on two. And I put a threshold point here. If I was capital T or small t, I'm going to predict I'm going to be taken. But if I was a small t and I predicted I am taken, but I turned out to be not taken, then I'm more inclined to move to the other territory, which is not taken, right? So you see, you basically move from here to here or here to here based on if your prediction was wrong twice, not one. Why do we want to do this? Because if you go back to the previous one of the main problems we had here is that I was switching too soon. I was switching that, okay, I'm wrong, switch. But once you switch, turn out to be wrong again, right? In reality, this is not even the pathological corner case. I can give you a worst case scenario that you be wrong 100% of the time, right? For example, if this was 2 and this is 1, right? So in that case, you can be wrong 100% of the time because once you switch, well, the program also switches, right? So that's the pathological corner case. To avoid that case, in the 2-bit saturating counter, I don't move once I turn out to be wrong. I'm wrong, but I'm going to hold it in my decision for another pattern. So you have to be proven wrong twice to switch. How to do this is, again, through this kind of notation of capital versus small. If I assume I was taking capital, that means my previous two were taken. So I was correct 2 times. Then even if I turn out to be wrong, I move here, not here. So you are still in the taken territory, but with less confidence right now. Make sense? So let's see how this really works in our previous example. So I just put the code back in to remember it. So I start with the same starting state, not taken, not taken. Now the actual outcome of the J was taken. So I turned out to be wrong. But I don't switch immediately. So in that case, I switch to small n, right? If you switch to small n, your prediction will still be not taken because you are still in this territory, right? And now you are taken, so you are wrong. So you are wrong twice. Good. Now, if I'm wrong twice, I move from small n to small t because you keep moving in that direction right now. You were here, you were wrong once, you come here, and then you're wrong twice, you come here. Good. If I'm small t, I'm going to predict I am taken. In that case, it's correct because that's the third J, right? In the third J, you predict you are taken, so you move from T to capital T, and then you predict you are taken, but then because you finish the J, you go to I, you turn out to be wrong. But now, here is the benefit. I don't switch from taken to not taken immediately. I'm going to move to small t back again. Because I was here, I turned out to be wrong, so I go 1 step back. Good? The benefit of this is now you still predict it's taken, and you are in fact taken. So you go back to capital T and you are correct. So over the steady state, if you ignore the initial point, over the steady state, what is your accuracy rate right now? 75%, right? You improve yourself by a factor of 100% from 50% to 75%, right? So why? Because you avoided the corner case of moving from the loop J to loop I, right? Because of holding on into the confidence before you switch your opinion too fast. Make sense? Good. Okay, so that's for a branch type prediction. Then there is this idea that we discussed in the tutorial also, because this was Maxim implements the G-share predictor is in fact a correlated predictor. We said the past two ones deal with branches as if they have no correlation. So I look into one branch type, I keep track of it, BEQ, for example, versus BEQ. But then most of the time, there is an interrelationship between branches. So I need, if I really bring this awareness into account, I might have a better decision, right? So in our earlier example, I had the I and J, they are different branches, but they are correlated. If I say these are two different branches, but they are still correlated, it's better than saying, I don't have the semantic that these are two different or the same, I just deal with them the same way, right? So the main difference again between local branches and global branch prediction in a global or correlated branches is you have the semantic that these are two different branches and they are correlated. Good. So how to do this? So simply, I keep a state of how many bits is still using. It's simply you have, well, in addition to you still have the 4 bits of the state, but now they are not for the same branch back in the history twice, but they are the direct previous execution of the 2 different branches. I don't know if that makes any sense to you. But if we go back to our program here, right now, what we said for this small thing is these, for example, are BEQs. Let's say they are BEQs. So I say I track the history of the BEQ. In the case of the directly past execution, it's the BHT, the single bit predictor. If I take the past two executions, like similar to what we do here, this is a 2-bit saturating count, right? But if I say, okay, no, these are two different BEQs, these two, for example, and then instead of taking the best two, or maybe it's a BEQ and BNEQ, like not equal, or any other B branch equals 0, BZ, any type of other branch, then in that case, instead of taking the best two in the history, I take the immediate past for this one and this one, right? So it's still 2-bit, but what they track is different. They track the directly past one of two different branches instead of tracking the past two of the same branch. Okay, this is why it's correlated branch. Okay. So here, that's why you still have 4 possibilities. Then you say, okay, if assume that pattern in the past was NN. This is also another thing that explains to you how really, in fact, your previous, remember this pattern time was my previous occurrence, right? The one that happened now, in the future is going to be one thing. In the past, in the 2-bit saturating counter, this was a single thing, right? If you go here, it was either N or E, right? Because it's related to one branch. But here, I'm separating them. I'm saying one of them was N, the other one was N, or one of them was T, the other one was N, right? So you basically keep the semantic of the two branches separated. And then assume your initial state is all N, doesn't matter. So in that case, your prediction is N. Well, again, my first J is true, so I turn out to be wrong. This one, in this example, behaves very, very bad because, again, with regard to the correlation, the J and I have different loop iterations, like bound. So in that case, they behave completely different. So the correlation doesn't work very well, right? And for that reason, what we said earlier is in the tutorial is it's better to keep the local and the global, and then you take the best decision. How do I take the best decision? I look into some window of time, then see the accuracy of both. And if one of them is behaving better than the other, I take that one for that window of time. Applications over time, they behave differently. For example, right now my application had this for loop that we had earlier, then this correlated one is going to be too bad. Later on, it might have two different nested loops that are really works together very good. In fact, in if statements, this is where correlated branch comes the best. So if later on in your code they have if statements, then the correlated one will be better than the PHD, and then you switch to the correlated one. Good. But this continues how the correlated one really works. Why it turns out to be like that. So I predict it's not taken, but then the outcome is taken. Right now, this is the J1. So I update the J1, but I leave the I not taken. Good. So in that case, I'm NT. NT, because I have 4 states like NN, NT, and TT. NT was, in the past it was not taken, and current is also, I predicted it's not taken, so it turned out to be N, so I have to correct myself. So, yeah, it was NN, my prediction was N, it turned out to be T, so I have to correct that one. So I did this to T. Right now, what is the directly previous state of the two branches? One of them was taken, which is the J, and the I is still not executed at all, so it's still N. So I have to pick the prediction from the state of NT. So my current state in NT is this one, so I'm going to predict it's not taken. I predict it's N. I'm still in the J, right? Because I executed J only once. But J turns out to be true. So I'm wrong again. What do I need to fix? I need to fix the NT state. So I move it from N to T. Okay? And then right now, I still have NT because I didn't execute yet. In NT, well, at least that's not my time. So basically the outcome is TT, so I have to move to TT. If this is TT, then I have to pick N again. I'm wrong because the last execution of J is true, right? So in that case, I turn out to be wrong. Then, okay, I have to fix the TT, so I fix it. Right now, again, I'm TT because the past, these two were TT. Then in that case, wow, I go here, I fix myself T, I predict I'm T because it's already T. Well, I've already moved over J to I, right? So my prediction is wrong because the J will be wrong. Why I'm going through all these steps one by one? because this tells us when this might work better. What do you think? Why, first of all, ask the earlier question. Why this one works very bad here? Basically, the direct kind of statement is, it takes time to build a table, right? Why? Because you have 4 different states you need to update. In the past, we had one that simply, even in the 2-bit saturating counter, I move directly from T to small n, so it takes me 2 steps to correlate. But right now, I have 4 different states. So it takes me some time to build up the correct semantics or the correct testimonial of the table, right? The problem right now is once you reach to that point of updating everything, the J is already done, right? Because J only executes 3 times. It takes me, in fact, 4 steps in worst case to fix everything. So if your pattern of execution is not long enough to keep you build the right history, then your prediction will be wrong most of the time. And that's one of the any speculation, I told you speculation is the predominant technique in computer activity. So a very important point that comes to prediction is it's a trade-off in the design, how you make your point. And maybe we are going to stop here and then we will not have the multi-site in the midterm. So the point is, if you don't give yourself enough time to build in the history that gives you the actual consensus of the program, then your prediction will be wrong most of the time. So there is a trade-off between how much time it takes you to build the history versus your accuracy, right? If the pattern is easy, you don't need a lot of history to reach the pattern. For example, if this was a million, like if the J and I was million and million, then in fact, well, my pattern is very easy because I would be wrong only twice at the beginning, and even 1-bit saturating counter will behave very well, right? But if this thing is the changing base of the program is very fast, then I need to build in a pattern for some time. If the change does not give me the time for that pattern, building time, I'm going to be wrong most of the time. Because once I build the pattern, I predict I'm wrong. I need to recorrect again. I take the same time. So it doesn't really work. And this is why also we have multiple predictors, and then you pick among them. Because some of them take a lot of time. Some make a very quick prediction, but it might be wrong. If the changing base is too fast, then you pick the one that predicts very fast. Even if it's wrong, some of the time it's better. If the changing base is too slow, then and it's a complex pattern, in that case it's better to build the history, and your prediction will be better. Good. Thanks for this, and see you in on Tuesday after the midterm.